Recording is rolling. It's Wednesday, August 17th. And yesterday I gave you guys a bunch of notes on trigonometry. Here, let's look at a bigger context. So I wanted to take this week to cover the math and basic science that you're going to be using all throughout the year. Monday we did some algebra. Tuesday I was going to do trigonometry vectors with you guys. Now, all this stuff about SI system, dimensional analysis type stuff, we're going to bump that to tomorrow, I think, because need some extra time with this trigonometry and vectors. So I gave you guys a bunch of notes. You guys remember SOHCAHTOA, whatever sine cosine relationships, tangent. Show you guys how to get an angle if you have sides. You guys remember like inverse tan, like inverse trig. And then I did a couple of these with you guys, and then I started on one of these, and then that's where we ran out of time. So let's do this. I'm going to flip my screen over. Say present screen 2. Right, and let's look at, I'm going to scroll through this animation. So we're going to do a quick review on, look at that, scalars and vectors. Remember, those are two categories of quantities that we're going to be doing and using in physics. Now, a scalar is something that has a magnitude to it. For example, mass. Right? If something has some amount of mass, some number of kilograms, if you take it into deep space, does it have the same amount of mass? Yes, it does. It's not amount of stuff, amount of inertia. But what does a vector quantity have that a scalar quantity does not? Some kind of direction. Yeah, some kind of direction, right? Which ends up being really important for vector quantities. Right, let's look at some examples. Oh, hey, look at that, 3 meters to the right. So like some number, some unit. Right? Units are important in this class in some direction. Let's make it a vector. Right? See, like a scalar would just say like 3 meters, but it says like to the right. Sometimes the direction is implied, but directions are going to be important. Right here. All right. Very good. All right. So how about this? Suppose you start off on the left side of that arrow. That's a vector, right? And you walk 3 meters to the right, and then you turn around and walk 2 meters back to the left. Ooh, see how those vectors are connected tip to tail? Remember that yesterday I was telling you guys about tip to tail vector connection, right? All right, so who can tell me from the point that you started to the point that you ended, right? 3 to the right, 2 to the left. What is your displacement overall? What is your displacement? You guys gonna say 1 meter to the right, 1 meter to the right? There it is. You guys see that pink arrow vector? That is, what is that vector called? It starts with an R. It's called the resultant vector. You guys remember that? Resultant. Right. So if you connect a bunch of vectors tip to tail, then if you go from the tip, from the tail of the first one to the tip of the last one, that is like the net effect. That's your resultant vector. So 3 to the right, 2 to the left, your displacement is 1 meter. Okay, so that's all fine, good. Now, what if you drove this around in your car? What if you drive 3 meters to the right and you turn around and drive 2 meters to the left? Doesn't your odometer add everything up? So what distance does your odometer say you went? 5 meters, right? But distance is a scalar quantity. Oh, look at that. So displacement's a vector, distance is a scalar. Right? It's a similar story with velocity versus speed. So velocity is a vector, speed is the scalar. Sometimes I might accidentally use those terms interchangeably, but yeah, well, there you go. That's the difference, right? Now, all the physics equations are all going to be in terms of vectors. So like even like sneak preview to like next couple weeks of stuff. See that green poster over there as those kinematic equations, like x equals b not t plus f h squared is the top one, right? See those 3 equations, right? If you plug in numbers to those equations, apply those equations, they naturally give you vector solutions. So they would tell you like displacement, not distance. Right? It's just distance. Right? All right, what else we got? Let's go to 2 dimensions. Oh, these all have units. Yay. Okay. What if you go 3 meters to the right and then you walk 4 meters up? Let's say like 3 meters east and 4 meters north, for example. Right? So from beginning to end, you can figure out what is your displacement. 3 to the right, there's 3 east, 4 north. You guys know your special right triangles? 5 meters. 5 meters? Because isn't that gonna be like a 3, 4, 5 right triangle? Is it? Hey, that purple vector is called a what kind of vector? resultant. Yeah, right. Okay, so if you want 3 east, 4 north, say like walking around a campsite or something, right? Yeah. Okay, there's Pythagorean theorem. Right? That's how you can figure out it's 5 meters. But if you know your special right triangles, I mean, 3, 4, 5 right triangles is pretty common type triangles, right? Okay, but you could use Pythagorean theorem right there to figure out what it is. Right? So 5 meters displacement. Hey, if you went 3 to the east, 3 meters east and 4 meters north, what distance did you walk? 7 meters. Okay, so the displacement's 5 meters, the distance is 7 meters. Right, guess that. Okay. In this class, we usually care a lot more about displacement than distance. Right? Oops, that was my next question. You guys see that angle in the bottom left corner? I actually gave away the answer if you're paying too close attention. How do you solve for that angle if you have a bunch of side information? Yeah. Yep. There you go. All 3 of those will work. So you need an inverse trig function. There's inverse tan. Now, if you play off inverse tan, see how they're doing 4/3? So that's like playing off the legs of a right triangle. Whenever you're doing legs, 2 legs of a right triangle has something to do with tangent. In this case, inverse tan to get to the angle. Okay, you guys remember that? And finally, can you add together vectors in any order? What if instead of going 3 meters east and 4 meters north, what if you went 4 meters north followed by 3 meters east? Do you still end up at the same final location? Yeah, right. And that's what they showed here. Okay, so when you connect vectors tip to tail, you can connect them together in any order, and that purple resultant vector is still the same. Right? How about this? What if you you're walking around a campsite? What if you follow that crazy path? So in the end, you want to just walk northeast. You guys see how the purple resultant is just like northeast, right? Say like campsite A to campsite B, but maybe it's like a crazy winding path through the woods. Like, so we're going to do blue. I forgot my colors. Right? Fell kindergarten, but here I'm teaching high school. Blue followed by red, followed by green, followed by yellow, and then the purple resultant tells you, okay, you started here and you ended here, right? But what if you followed those vectors in a different order? So they're connected tip to tail, but let's try this. You guys like that animation? So what if you did yellow followed by green, followed by red, followed by blue? Did you guys notice those vectors moved around, but they did not actually change orientation? They didn't rotate. They just like slid around, right? Right. Okay, but the purple resultant, it's still the same. Let's see one more. Green followed by red, followed by blue, followed by yellow. It's still the same purple resultant. You guys get that? Right. Now, for this whole video animation, he's been using displacement as an example. So this many meters, right? But you guys know a few other kinds of vectors. Hey, is force a vector? Can you guys measure force in newtons? Hey, you guys remember the monkeys pulling the bananas? Right? You guys remember those 3 monkeys? Right. So do you think you could do the same tip to tail vector analysis with the monkeys pulling the bananas? Would it matter which monkey you considered first pulling the bananas? No, you can consider them in any order. Right? All right. So that's some of the stuff you guys saw yesterday. Let's flip back over to where's my mouse cursor? Right. Back to this. Okay, so we're looking at here. You guys remember at a glance, this looks like a right triangle. It is a right triangle, but if you look a little closer, let me zoom in here. You say, oh, actually, this is like some kind of vector pointing up to the right that's labeled z. And it looks like it's being broken down into components. That's why the legs of the right triangle are dashed, and they all have arrowheads on them, right? So it looks like a vector that's been broken down into components. Hey, you guys remember that hungry monkey that was pulling kind of up and to the right? Right? And then at some point, you can look at your notes and remember this too. You're going to figure out, well, how much to the right and how much up was that monkey pulling? You guys remember that? Yeah. So we did all this, right? So if you know a little bit of information about a triangle, you can figure out everything else about a triangle. As long as you have a critical minimal amount of information, you need 3 pieces of independent information too. Right? So one piece of information is the right angle, and then I gave you guys 2 other pieces of information. Right. So you got these. Let me do one more of these with you guys right now. Let's do number. Let's do number 6. Number 6. Oh, it looks pretty fun. So I gave you one of the acute angles and one of the legs of the triangle. Ooh, right, one of those components. Right? So who can just look at this page and tell me what alpha is? What is alpha? 20 degrees. How'd you know it was 20 degrees? Yeah, because alpha and beta for a right triangle these two acute angles have to add up to 90 degrees, right? As long as you have a flat triangle, right? So I'm gonna draw this out at this point. Right? So I got this vector up and to the right, labeled z, and then that's broken down into x, y components. So dash these off, dash, dash, right? And what else do I? Okay, I know that this angle is 20 degrees. You guys just told me that. I know that this top right angle beta is 70 degrees because that was given. And the other bit of info is given is that this x component says 22 kilometers on my page, 22 kilometers, right? And at this point, we don't know what y and z are, but it's some number of kilometers, right? So let me attach a story to this in case that helps at all. It looks like what happened is maybe there's like a big old field, right? And I'm walking from this corner to this corner. This looks like probably like marathon length, maybe, right? Or actually not exactly that far, maybe like half of that, right? But pretty big distance. So I'm walking like northeast. See, I'm walking northeast, right? How far did I walk northeast? Well, I don't actually know. I don't know how far I walked, right? But I do know the angle, like the direction I was walking, and I know my change in my maybe like a east-west coordinate, my change in longitude, right? I don't know the distance I walk, and I don't know my latitude change, but we can find those out. Right? And there's multiple ways that you could approach this. Let's start with what do you use myself for first? Y or Z?
Y.
Y? Let's do Y. Okay. Now, if you do Y, what's one relationship that you could set up to solve for Y? Yeah. Okay. So tangent relationship, because the two legs of a triangle have something to do with tangent. We want one of the legs, and we have information about the other leg. So definitely something with tangent. Okay. So how about this? Tangent of here. I should ask you guys what's going to make the easier fraction, but I started to write the number. Right? You guys see I'm starting to pick the 20 degrees. Right? Tangent of 20 degrees. There's a reason I chose that angle, because that's equal to what over what? Opposite over adjacent. Y over 22 kilometers. Isn't that true? Okay, and we're solving for y. Okay. See, you could have said tangent of 70 degrees is 22 kilometers divided by y, but then what you're solving for is in the denominator. It would just be one extra algebra step. Could have done that. Okay. But we're one step away from getting the answer. What's the one algebra step? Can you cross multiply 22 kilometers? Can you say y is equal to 22 kilometers multiplied by tangent of 20 degrees? Can you do that? Yeah. So 22 kilometers, tangent 20 degrees. If you brought your own calculator, make sure your calculator is in degrees and not in radians. So your calculator needs to know that you're using degrees. Before I hit enter, let's estimate what would be a reasonable answer to get, because that's a good thing you do in physics, is check your answers. But does that look believable? So even before should y be greater than or less than 22 kilometers? Less than. How'd you know it was less than 22? This is a real skinny angle, isn't it? Right? My picture is not quite sure proportionate. This should even be like a skinnier triangle. Right? Right. Let's see what it is. 8.01. Y equals 8.01 kilometers. Okay. Realistically, you might know like 8.0. That's probably as much as you can know. Right? So 8.01, I'll call it. Okay. All right. So now we know everything except for the actual distance we walked. So I'll fill this in here, 8.01 kilometers. Okay. What's one way to solve for z? Sure, Pythagorean theorem. Okay. It's not the only way, it's one way. I'll do two different ways with you guys. Let's do Pythagorean theorem. Can you guys say z squared equals x squared plus y squared? Which, just save myself a little paper room. I'm gonna go ahead and write the numbers in. That squared plus that squared. Can I do that? Okay. And then now let me see what this all comes out to. It's 22 squared plus 8.01 squared. So z squared is, so this all sums to 548.16 square kilometers. Right? Now, really, that's way too precise, but that's okay just as a middle step. Right? Say some digits for middle steps. Right? What's the very last algebra step? You guys thinking square root both sides? Square root both sides? Do you also get square rooted? Oh, did I tell you guys a fancy way to take a square root with a power? Square root, same thing as the power of what? Power 1/2. Yeah, right? Power 1/2. Okay. So watch this. Caret 0.5. Boom, done. So caret 0.5, it's a square root, same thing. So that's 23.4 kilometers. Okay. Oh, I meant to ask guys before I actually solved that. What do you think would be reasonable? So see, this came out to 23.4 kilometers, 23.41, I guess. 23.4. Hey, that's interesting. The distance I actually walked is only a tiny bit more than the longitude change. Look at 22 compared to 23.4. Is that right? Look for that in the future. Anytime you have a pretty small angle, 20 degrees, that's kind of smallish. So usually hypotenuse is not much bigger than the longest leg of the trunk. Right? Is that? Now, just to extend this a little bit, let me show you guys a different way you could have solved for z. Okay. You could have solved for z from the outset, even before you got y. Could I say this? Could I say that tangent? No, scratch that. Wrong one. If I'm solving for z, I definitely do not want tangent. That'll never get me there, right? If I'm playing off 20 degrees and the 22 kilometers I'm solving for z, is this, and this have a what relationship? Sine or cosine? Cosine. Because this leg is touching the 20 degrees, which means cosine. So I need cosine. Cosine of 20 degrees is adjacent over hypotenuse. So that's 22 kilometers divided by z. Okay. Now you guys know what z is already. It's, oh, I forgot my unit. Kilometers. So kilometers, right? Okay. So you know what the answer is already. I just want to show you guys that this does work out. So I'm going to cross multiply the z cosine 20 degrees is 22 kilometers. Hey, that's like the notes I gave you guys yesterday. Remember, hypotenuse times sine or cosine is one of the legs. Okay. And then divide down the cosine. Z is equal to 22 kilometers divided by cosine of 20 degrees. I hope this comes out to 23.4 kilometers, because that's what we were getting using a different method. What's 22 divided by cosine of 20 degrees? It is 23.4 kilometers. Oh yeah. Math works. All right. Guys good there? And so a few different ways you can approach that. There you go. Right, so now we've got 3 of those done. Yay. Right? Guys good? All right. Let's take a look at this side. Okay. So I gave you guys 5 triangles and a table with 5 rows. 1 row per triangle. So each row refers to one of the triangles. Is that? And if you go across the hovering over the top of the columns, you guys see it? Some of these it says measure, and some of these it says calculate. Right? Okay, so we're going to make some measurements. That's the science portion, right? Like empirical observations. Okay? And then for all the calculations, we're going to pull up the calculator and see how close these align. Right? So let's start by getting the measurements. Looks like 5 measurements, a couple of angles, and then the 3 sides of having you guys measure. So I started on Maxwell triangle yesterday. So pick up where I left off yesterday. Okay. I got alpha was 22 degrees. Let me remind you guys how to do that. So take the node of this protractor, park it right on this corner, zero out the leg, and this actually sweeps through 2 numbers, 22 degrees and 158 degrees. But you guys know that alpha and beta are each less than 90 degrees. So the only one that makes sense is 22 degrees. Okay. 158 is this huge obtuse angle over here, which is not what we're interested in. Okay. Okay. How about beta? Now, you could measure clockwise or counterclockwise on this. Here's the other way you can measure alpha. Park this right here, zero out the hypotenuse, and then this leg also sweeps through 22 degrees. So it's okay. Okay. Now, let me get beta. So I'm going to take this node of this protractor, park it right on this corner, zero out the short leg, and then the hypotenuse will sweep through what the angle is. Right? Because remember, a protractor measures angles, so it's like, what's the size of this wedge? How big is this wedge? Okay. The Maxwell triangle is just barely big enough for this protractor. This looks like, I'm reading 67 on this, I think. Right? Well, or 113, but that didn't make sense. So it's got to be 67. Okay. So I'm going to write 67 degrees here. Okay. Tell you what, let me do a couple things. If your triangles are too small for your protractor, it's kind of small triangles, kind of big protractor. What could help is to go ahead and just extend the legs, like extrapolate. And I did that kind of with that one yesterday. So go ahead and extrapolate all these. Okay. Putting a hypotenuse. Okay. So then your leg extensions will run through the numbers on your protractor, and you're like, okay, I can get the size of those wedges. Okay. But the other way I could have gotten beta is to turn this whole thing upside down, zero out the hypotenuse instead. Okay. It's fine there, that's zeroed out. And then this leg extension also sweeps through. Okay, well, here I'm looking at 68. So, 67, 68, it's somewhere in there, right? Okay. Different ways you measure it, you might get plus or minus a degree. Now, what do my alpha and my beta add up to? Is that 89 degrees? 89 degrees, is that right? Is that okay? Huh. Well, it depends what class you're in. If you are in a math class, is your math teacher going to count off if they only add up to 89 degrees? Yeah, your math teacher would count off because they ideally should add up to what? 90 degrees. Okay. But since you guys are sitting in a science class, science has a little bit different philosophy. What do you think is more important in science? Your empirical observations and measurements or textbook theory? What's more important in science? Your observations. Yeah. So they should add up pretty close. If you get anything between 88 degrees and 92 degrees for the sum of these two angles, then that's close enough for this class because it's a science class, and that's the right. So I'm okay with that. Right? If you want to do multiple measurements, then and make sure they add up to 90, that's okay. Right? But what you should not do is say, well, those that don't add up, so I'm just going to erase one and force them to add up, going against my own observations. Right? That would be not what you not good for science. Right? We got to measure the three sides, C, A, and B. So I'm going to break out this ruler, measure what is side C. You guys remember, are you using centimeters or inches? Centimeters. In fact, it even specifies the unit, says how many centimeters. So go to centimeters. That looks like, I'm going to call it 6.8, I think. 6.8 centimeters. If you got something slightly different from me, then that's okay. If you got 6.7 or 6.9, write that. I'm going to say 6.8. What is side A? 2.7, I think. 2.7. Right. I think sometimes I measure that and get 2.6. I got 2.7 right now, so I go with that. Then, okay, no, those are all measurements. Measure, 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 measure. Then skip a few cells, and there's one last measurement. This will make sense why this table is organized this way here in a few minutes. If you don't see it yet. Okay. So what is side B? That looks like, I think we call it 6.4. I'll call it 6.4. It's pretty close to. Okay, great. Now I'm done with the measurements. So all your triangles, first four cells are measurements, then skip a few, and then get side B. Okay, now it's calculator time. So what do we got here? This first calculation says C times sine of alpha. Now, before you just get plugging and chugging, think about what that means. Right? See, if you start with your hypotenuse C, and then you multiply that by sine of alpha. This was in your notes yesterday. Oh, it's right here. Right. If you take your hypotenuse, multiply by sine of alpha, doesn't that kick over to the opposite side? You guys see that? Right. This is really good to know. Right. Everything boxed in right there. Really good to know. All right. So, okay, so this looks like a different perspective on how you get side A, which we've already measured. You guys said the direct measurement was this. So I sure do hope that this calculation agrees with that measurement. Let's see if it does. Take C, 6.8 centimeters, times sine. See, alpha was 22 degrees. Oh, don't mix up alpha and A. You guys see, alpha and A are completely different concepts, different units. So alpha is 22 degrees. That is 2.55 centimeters. Right. Ooh, that is extremely close to what I measured. You see that? Okay, so I'm happy with that. Next one, c times cosine of beta. So that's 6.8 centimeters times cosine of my beta was 67 degrees. That is 2.66, which actually does round to my measurement. So that's definitely good. Right? And then what the heck is this? Square root of c squared minus b squared? Where's that coming from? What's that about?
That's the equation to find a squared.
Ah, yeah, that's just a different perspective for a, going through the what theorem? Pythagorean theorem. So I bet a lot of you guys remember that from yesterday. In case you don't, let me write this real fast. You guys know how a squared plus b squared equals c squared, right? Suppose you solve for a, 2 algebra steps, you can get it. What's the first algebra step? Subtract over b squared. And what's the other algebra step? Square root. So a is equal to square root of c squared minus b squared. Oh, that's exactly what that's us to do. See that? So let's try it out. Let's do square root of 6.8 squared minus, and now your b is over here. We measured that already. 6.4 squared. And what is that? 2.297. That rounds like 2.30. I'll call it 2.30. Rounds to. Right? Huh. Now that one seems to be the furthest off. You guys know that's also referring to side A, right? That one's off kind of a bit, isn't it? Right? Having done this assignment enough times over the years, the number that is usually furthest from your direct measurement does tend to be the Pythagorean theorem one, right? So that's okay if it's off of it, right? But do you guys see a very dark rectangle around these 4 columns? Because all 4 of those cells refer to the same side. You guys think the pattern is going to repeat over here? Like all 4 of these other cells are going to refer to side B, right? Okay. So I hope all these numbers are pretty close to 6.4. Let's find out if they are. What is c times sine beta? So that's 6.8 times sine of 67 degrees. That is 6.26, it rounds to 6.26. C times cosine alpha. So that's 6.8 times cosine of 22 degrees is 6.30. And square root of c squared minus a squared. Ooh, well, do you guys think if we had solved for b instead of a, that we get something that looks like this? B equals the square root of c squared minus a squared. Still comes from Pythagorean theorem, right? You guys believe that, right? Or see that? In fact, don't believe it? Try it out yourself. I bet you will get to that. All right. So square root of 6.8 squared minus, now here's a, remember, a and alpha, different things. So here's a, 2.7 centimeters being squared. That is 6.24 centimeters, 6.24, right? Which, okay. So interestingly, my 3 calculations are each a tiny bit less than my measurement, but they're really close. Okay. Is that right? You guys good so far? Right. I'm going to do one more triangle example with you guys. How about this curry triangle? Let's just curry triangle. So first measure the 2 angles. You know what? Before I get my measurements, let me go ahead and extend these legs. Right, so extend, 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 because this will help me get my angles. Okay, just extrapolate a bit, right? Because small triangles, big protractor. Right, so 2 ways to measure alpha. You can take this node, park it right on this alpha corner, zero out this leg, and then the hypotenuse looks like it goes through, what is that? Is that 52 degrees, I think? 52 degrees? 52 degrees, right? Or I could have turned this upside down, turn the protractor upside down. Still park the node on the alpha corner, but this time zero out the hypotenuse. And this leg now runs through, oh, it's still 52 degrees, 52-degree angle. Okay. So the size of this wedge is 52 degrees. Okay. Let's go grab beta and take the protractor node, park it right on this corner, zero out this leg right there. And this hypotenuse runs through, I'll call that 38 degrees. Looks like 38 degrees. Hey, what does my alpha and my beta add up to? 90 degrees, okay? Which is actually ideal, right? Remember, for science, as long as it's somewhere between 88 and 92, that's good enough. Now side C, which is the hypotenuse. Break out my ruler, turn it to centimeters. Measure, this side is, I'm gonna call it 5.5, I guess, 5.5 centimeters. Right. Side A, I'm gonna call that 4.3 centimeters. Then skip a few cells to get the last measurement. Remember, last measurement's way the heck over here. But once you see the table organization, I think you guys do. You see why that measurement's over there, right? Because right, all the calculations are going to refer to the side just from different points of view. This looks like 3.4, I guess. 3.4 centimeters. Okay, so that's all my measurements. 2 angles, 3 sides. Now it's calculation time. So remember the organization of this table. That dark outline rectangle indicates that these 3 cells each refer to the side, so they should be pretty close in calculation. Right? It's the same story with these 3 cells here, refer to the side. Right, so C times sine alpha. C times sine alpha, that kicks over to this side A. Yep, side A. So 5.5 centimeters times sine of 52 degrees is 4.33. Okay, notice real fast. It's 4.33405945. That's way too precise, but there's a point I'm about to make here. Next one, C times cosine beta. So 5.5 times cosine, your beta, okay, I'm looking at 38 degrees, 4.33. Not only is it 4.33, 4.33405945. Hey, that's exactly the same number as before, isn't it? Right. Now that didn't work out exactly on the Maxwell triangle, but did it on the Curry triangle? Right. Now why is that the case? Right. Because let's see here. Do you guys remember from a math class that if alpha plus beta equals exactly 90 degrees, like 90.00000 degrees, then sine of alpha is equal to cosine of beta? You guys probably remember that from like pre-calc or trig, right? And the other way too, sine of beta is equal to cosine of alpha, right? Which is exactly what we just showed right here, like down to the like 10 decimals under same number. Okay. Got a little tidbit to know. See, by Maxwell, the angle's only out to 89. It looks like I mismeasured a little bit, right? But here, 90 degrees. Right, and reverse Pythagorean theorem, square root of c squared minus b squared. So it's 5.5 squared minus 3.4 squared. That's giving me 4.32. 4.32. All right. Look at all those calculations align really well with the measurement. So that is good news. Right, last 3 cells on the Curry triangle. Now, these last 3 cells should all refer to side B one way or another. So C times sine beta, hypotenuse times sine beta, opposite of beta. Yep, that's definitely side B. So 5.5 times sine of, my beta was 38 degrees. That is 3.39. C times cosine of alpha, 5.5 centimeters times cosine of 52 degrees, 3.39. And finally, reverse Pythagorean theorem, square root of c squared minus a squared also gives me b. So square root of 5.5 squared minus 4.3 squared, 3.43. But 3 0.43. Aha. Okay. And these four values all round to 3.4, which was my measurement. So that's definitely good. You guys good so far? Who's got any question? Any question? All right. So how are we doing on? Okay. Right. So we got a solid 11 minutes of class. Looks like. Okay. Here's your guys' assignment. So choose 5 on both sides. Right now, the trig lab side that we're looking at right now, there are 5 triangles. So make all the measurements and do all the calculations. I see those work. Okay. And then on the side that's just pure math, right, that has the 10 different triangles, just choose any 5 of those. Right. You guys got the rest of class today, and let's have this due on Friday. We'll walk around the rest of class and help you guys out, answer any questions that you have. Okay, and end recording.